Hello everyone, so this is lesson 2 of lockdown. Today we're going to be looking at the structure and properties of chemicals and look to see how that affects their conductivity. So you're going to need the following. You're going to need your key area 2 book, you're going to need a data book, a pen and a pencil, and also some paper to do some of the questions that are going to appear. So we're going to start as we did last time with a little mini test. This is really important you do this. It will help you in the long term with the materials that we haven't done for a while. So 3 questions. It should take you around about 10 minutes. So as last time, you can pause the video when the question comes up and you can go through it at your own pace. So here's the first one. So just pause this whenever you're ready, and then once you've answered the question, you can unpause it and we'll go through the answer. Okay, so for the first one here, what is the average rate of reaction over time? So for this, we need to use the equation, the change in quantity divided by the change in time. Our time here is 2 minutes. The quantity, the volume of gas that's being collected, is 5. So our calculation is going to be 5 divided by 2. You put that into your calculator and you get 0.4. So the answer for question number 1 is B. In terms of the units, well, our volume is measured in centimetres cubed. Our time is measured in minutes. So we've got 2 possible options. It could be, well, it's always going to be the volume is going to come first. So that's going to be either A or B, and the correct answer for National Fire would be B, centimetres cubed per minute. The way that A reads is centimetres cubed per minute, so that one will be incorrect. Okay, moving on to the next question. Okay, so here's the next question. So if you want to just pause the video, and when you've got your answer, you can unpause it. So when an atom X of an element in group 1 reacts, it becomes X positive. So we've gone from an atom to an ion. That's what the plus symbol there represents. So in this case here, how do we become an X positive? Well, the way that happens is if the atom loses an electron. So if it loses its electron, it's now going to have more positive protons than it does negative electrons. So it's going to be a positive ion. So let's go down and have a look at what are the possible options here. So A, the mass number of X decreases. Well, the only way for the mass number to decrease is if the number of protons or the number of neutrons changes, and it hasn't. B, the atomic number of X increases. Well, if it increases, then we're not going to be talking about X, we're going to be talking about a different atom now. So that is not going to be the answer. The charge of the nucleus increases. The only way that the charge can increase, again, is if we have more positive protons added to it. So that doesn't happen when you become an ion. And D, the number of occupied energy levels decreases. Well, if it's in group 1, the clue is the group 1 here, then the atom is only going to have 1 electron in its outer shell. If it becomes X positive, that outer electron has been removed, so we have lost an occupied energy level, therefore D is the correct answer. Okay, next question. So this links into covalent bonding. So again, pause this when you're ready, come back to it. Okay, so for the first one, there's multiple different ways that you can do the diagram, but the way that we've been taught in school is using something called a dot and cross diagram. Chlorine is in group 7, so we've got 2 lots of the chlorine atoms in a Cl2 molecule. In group 7, the electrons, there are 7 outer electrons, therefore each chlorine atom wants to form 1 covalent bond. So in other words, it's going to want to share 1 electron with another atom, and it will look something like this here. So in the center there, we have the 1 shared electron from each atom, and then going around the outside, we've got the outer electrons, and the marking instructions there tell us that we have to have the outer electrons. So the next question, what is the name of the shape? Well, we've got an atom in the middle there, that carbon, that's surrounded by 4 other atoms. And the only one that this could be is a tetrahedral, or sometimes referred to as a tetrahedron. Okay, so that's our little quiz to begin with. Let's crack on with today's lesson. So the materials that we're going to cover today are to do with the conductivity and how the structure and property of a chemical determines its conductivity, whether it will allow electricity to pass through it. So we've got our success criteria there. Just take 30 seconds to read those and then we'll get started. So this gives us an idea of the sort of question that we can expect to answer. So the question says, which line in the table shows the properties of an ionic chemical? So we have 4 chemicals, A, B, C and D, and then we've got 4 things about them. We've got what their melting point, their boiling point, whether they conduct electricity when they're a solid, and whether they conduct electricity when they're a liquid. So we know how the structure and the bonding determines the melting and boiling point. We did that last lesson. But today we're going to look at how the conductivity can also help us identify whether a chemical is ionic, covalent or metallic. So hopefully by the end of this lesson we'll be able to answer this sort of question. And this is another type of question that similar type of question we have to answer at the end of this lesson. So state why ionic compounds like aluminium oxide conduct electricity when molten. So I'll show you these later on and you can have a go at them. So we learnt last lesson that if you have an ionic, covalent or metallic chemical, or rather we focus on the ionic and covalent ones, didn't we? You can have 3 different structures. You can have this huge ionic lattice where you have trillions and trillions of negative and positive ions, oppositely charged ions next to each other. You can also have a covalent network, which is lots and lots of individual atoms that are all covalently bonded together. Or you can have a covalent molecular where you have individual molecules, in this case it's H2O molecules, and they are bonded together. The atoms within the molecule are bonded together, but the actual molecules are not bonded together. We have weak intermolecular forces that hold them together. So last time we looked at how these structures can affect the melting and boiling point, and this time we're going to try and answer this question. How does the structure and the state of a chemical affect its conductivity? So we'll just go over the state aspect first of all, so let's just have a look at that. So you may remember from S1 and S2 we talked about solids and liquids and gases, and we want to be able to represent whether a chemical is solid or a liquid or a gas in a chemical formula or chemical equation to allow us to identify if it's a solid, a liquid or a gas. And the way that we do that is very, very simply. In this case we've got ice, that is water in the solid form. So if we have any solid chemical, we'd use an S in brackets, and we put that in what we call subscript, which is just sort of below, if you imagine a halfway line going through that H2O symbol, the subscript would go just below the halfway point. So that's S for solid, it is L for liquid, and it is G for gas. So fairly straightforward there. Any solid, liquid or gases, if we write the formula, we have to represent whether they are a solid, liquid or a gas using those symbols. But we have another symbol that we haven't come across before, and this is for chemicals that have been dissolved in water. So let's read this. When a solid is dissolved in water, we say it is in solution or it is aqueous. For example, I could get some solid copper sulfate and I can add that to water and it will dissolve. And if it dissolves, I'll form a solution. So we would then write the symbol there, AQ, below it. So that will be CuSO4, which is the chemical formula for copper sulfate, and then we have our state symbol below it there. So those are our 4 state symbols that we're interested in, and that's going to be useful for today's lesson. So to give you, and to go into a little bit more detail about what's happening with an ionic solid when it dissolves in water, is if you remember this lattice structure, when we add it to water, this happens. The lattice completely breaks up, and we have our negative and positive ions. Also included are some water, because the water is doing the dissolving, that's our solvent, and then we will form our solution. And these ions now are free to move around wherever they want to go. Okay, so our experiment that we're going to watch here, we're going to investigate how the state and structure of a chemical can affect the conductivity. The way that we're going to do that is as follows. So we would set up this circuit here, and our test substance at the bottom would be our chemical, whether it's an ionic or covalent or metallic chemical, and it would also have different states. That would be either a liquid or solid or in solution. And if it conducts electricity, then the ammeter would show a current flowing, or if we had a light bulb, the light bulb would light. So I'm going to show you a little video. I'm going to talk you through the video, and whilst you're doing this, I'd like you to go to page 45, and I'd like you to go through and fill out this table. So all you need to do for here is write down C for conductor or I for insulator in the appropriate boxes. And don't worry if you don't get all of them, because we will go through these later on after the video. let's just pause this here. So what's happened now, we have a lot of solids there. We have aluminium, we have C12H22O11, that's a covalent chemical because they're all non-metals. We've got sodium chloride, which is an ionic chemical, and then we've got silicon dioxide, which is a covalent network, and then we've also got water on the left-hand side. So if you can notice this here, of all of those chemicals, so the ones in the solid form, the aluminium, the C12H22O11, the NaCl and the SiO2, in the solid form, the only one that conducts is the metallic one. So we can conclude from this that metals, when they're in the solid form, they will conduct electricity, whereas covalent and ionic chemicals will not. So now they're all being dissolved, or rather water is being added to all of them, they're all being stirred. The aluminium is not forming a solution at all. The C12H22O11, that is not forming a solution either. Neither is the silicon dioxide, but the NaCl is. And what we should notice here is that when a solution is formed, the ionic chemicals can conduct electricity, whereas the other chemicals cannot. So now we have some more chemicals, and now we've got polystyrene balls there. We've got C2H6O, so that's another covalent chemical. We have copper in the solid form, so that's a metal, and then two ionic chemicals. And again, it's only the metal in the solid form that can conduct electricity. The covalent chemicals cannot conduct electricity when in a solid or in the C2H6O's form in the liquid state. And now it's going to be dissolved. The polystyrene balls will not dissolve. The C2H6O will form a solution. It will be immiscible with the water. It will mix with the water. The copper will not form a solution, but the calcium chloride and the copper sulfate, the ones on the right-hand side, they will. And just like last time, the ionic solutions will conduct electricity, whereas the other chemicals will not. Okay, so this video here is going to show what happens when you put electricity through graphite, which is carbon, so it's a covalent chemical. So it's going to be put through a pencil.
Alright, about to do another pencil burning experiment. A 4-cell and 5-cell LiPo battery are connected in series together. We're getting about 37 volts there right now. And we're going to hook it up to the pencil. This is about 80% to 100% more voltage than our last experiment with the 5-cell battery alone. Try to get this positioned. Zoomed in. Hey, this should be really exciting with that much voltage going through there. Hooked it up. And sparks are gonna fly. That's smoke. Much faster. That's smoke coming out. That was 2.7 meters. That's not too bad. Oh, pencil's on fire. And not enough to combust. Look at that. And the element is glowing. It's so hot it's glowing. That's what I wanted to see. And it broke. The experiment's over. That's what I wanted to see. And it broke. The experiment's over.
Okay, so there's our two experiments. We had metallic and ionic covalent chemicals in different states conducting or not conducting electricity. Can you have a go at this table on page 45 if you didn't already finish it? And can you also do your conclusion, and then in a few minutes time, once you've done that, unpause the video and we'll go through the results. Okay, so what we should have found is that with the solids, that was the aluminium and the copper, they did conduct electricity both times. Now, we could melt that copper, we can melt the aluminium, and we would find that in the liquid state they would also conduct electricity. So any metal, whether it's a solid or a liquid, will conduct electricity. And we don't have metallic solutions, they don't dissolve in water, so therefore that box is blacked out. For the ionic chemicals, we should have found that in the solid state that it did not conduct electricity. So that was sodium chloride, it was copper sulfate, copper chloride as well was there, I believe. In the solutions, when it was dissolved in water, it did conduct electricity, and we would also find the same thing if we heated up our ionic solids to its melting point and turned it into a liquid. It would be a conductor. For the covalent chemicals, it didn't matter whether it was a solid, a liquid, or in solution, it was always an insulator, with the exception of graphite that we shown in the second video. So those are our results, and here's our conclusion. So we should have found that the solid conductors have metallic bonding. Carbon in the form of graphite is an exception, as it has a covalent bonding. Liquid conductors have metallic or ionic bonding. Solutions which contain compounds which have solutions which conduct contain compounds which have ionic bonding. And covalent substances never conduct except for carbon. So what we're interested in now is actually going into an explanation as to why that happens. So that's what we're going to cover in this next section. So those are our results for the experiment as to whether something conducts, if it's a metal, or if it's ionic, or if it's covalent. And what we're going to go through now is an explanation. So I'm just going to let you read this, and then we'll look into metallic, covalent, and ionic chemicals in more detail. Okay, so let's look at metals first of all. So all metals would conduct whether it's in the liquid state or whether it's in the solid state. And if you were to look at a metal on the atomic scale, what you'd see is you see this lattice, so this is a solid, you see this lattice of positively charged ions and something called delocalized or freely moving electrons going around each of the ions. So we have positive metal ions and we have freely moving outer electrons, and it's those freely moving outer electrons that allows metals to conduct electricity. So freely moving charged particles, in this case electrons, therefore metals are conductors. So let's move on to the next one. So here we have our ionic solid. Now an ionic solid is in the lattice structure and the ions are not free to move, which is why ionic chemicals don't conduct electricity. However, if they do break up, if it dissolves or if it melts, if the lattice breaks up, then our ions are free to move. They can go wherever they want to. So because we now have freely moving ions, we have conductivity. So let's have a read of all the text there, please. And lastly, covalent chemicals. So the covalent chemicals we tested in the first experiment, none of them conducted, therefore none of them have freely moving charged particles. However, in the second video, the graphite did conduct. That leads us to conclude that it must have freely moving charged particles, and in this case the charged particles are electrons. And if we were able to look at graphite on the atomic scale, it would look something similar to this here. So the black spheres, they represent carbon atoms, the blue lines represent the covalent bonds between them, the dashed red lines represent the intermolecular forces between these sheets of graphite, and somewhere in there, it hasn't been shown on the diagram, but somewhere in there we also have freely moving electrons going around each of the carbon atoms, and it's those freely moving electrons that allow the graphite to conduct electricity. So I'd like you now to complete pages 46 to 48, and then after that we have some past paper questions to go through. Okay, so we showed this right at the beginning of the lesson. So which line in the table shows the properties of an ionic substance? So think back to last lesson and today's lesson, pause the video and have a go at the answer. Okay, so we can focus in on either the melting, boiling or the conductivity of solid or liquid. So let's have a look at, well, it's an ionic substance. So we know if it's an ionic substance, it's going to have a melting point and at least 500 degrees Celsius plus. Anything below that isn't going to be ionic. So that immediately, we can count out A. A is going to be a covalent chemical, and our evidence for that is the low melting and boiling point and also the fact that it doesn't conduct electricity. For B, B has quite a high melting and boiling point, but so let's have a look at the conductivity. As a solid, it doesn't conduct electricity, but as a liquid, it also doesn't conduct electricity. So therefore, it can't be B. For D, D has a high melting and boiling point. It conducts electricity as a solid and as a liquid. So the fact that it conducts electricity as a solid must indicate that it is either graphite or that it is a metal. In this case, it is a metal. That leaves us therefore with C as the correct answer, because it has a high melting and boiling point, doesn't conduct when it's a solid, and does conduct when it's a liquid. Next question. So this is a near identical question here, but it's from a different year. So this sort of shows you that these type of questions are repeated again and again by the examiner. So again, pause this and have a go at this question, please. Okay, so we're looking now for a covalent network. If it's a covalent network, it's going to have a very high melting and boiling point. It's not going to conduct electricity, either a solid or a liquid. So the only chemical that could be is therefore D. It can't be A because the melting point and boiling point are too low, even though it doesn't conduct electricity as a solid and a liquid. Next question. So state why ionic chemicals like aluminium oxide conduct electricity when molten. Pause and then unpause when you're ready. So hopefully you've got written down that the ions are free to move, they're able to move, or they are mobile. And if you want to pause this and then just have a look through the, on the right hand side, it gives you the key information that you need to include. Okay, so have a read of all this, and when you're ready, that's us done. So today we've written state symbols for chemicals, for solids, liquids, gases, and also for solutions. And then we've predicted and explained the conductivity of compounds based on their structure, bonding, and state. If you guys can have a go at the corresponding worksheet, that would be brilliant, and we'll get that back to you as soon as possible. Thanks for watching.